variation of temperature. Okay, so if temperature variation is there, so energy transfer takes place in a media. So that everybody knows. And we know that there are three modes of heat transfer. So that is conduction, convection, and radiation. So three modes of heat transfers are there. And if temperature gradient exists, then heat transfer takes place. So when conduction mode of heat transfer takes place, you know these things. So when heat is conducted in solid or heat is conducted in fluid at rest, and definitely temperature gradient exists. In that case, heat transfer mechanism is called the conduction mode of heat transfer. Okay. So who is responsible for conducting heat? So everybody knows that is your thermal conductivity is responsible. Okay, understand my points? Hello?
Yes, sir.
Very simple.
Yes, yes, sir.
Sure. Yes. So that means here, conduction heat transfer, heat is conducted in solid or in fluid at rest. So definitely temperature gradient should be there, temperature variation should be there, and during this design condition, heat is conducted in solid or in fluid at rest. So definitely thermal conductivity is responsible for that. Okay, so K, that is your thermal conductivity, which is responsible for conducting heat in solid or in fluid at rest. So definitely you should mention at rest condition in case of fluid. So K is there, that is your thermal conductivity. You know, it is a material property of a solid. So K is a material property of a solid and K is a thermodynamic or thermal property of a fluid. Okay. And you know, if we concentrate on the transfer in solid, then K is there. So definitely K is the thermal conductivity and it has two components. So everybody knows these things. The thermal conductivity for solid has two components. One is electronic components and another one is lattice component. So two components of thermal conductivities are there for conducting heat in solid. So better here you can see on this board that is K is the thermal conductivity and it has two components, you know, K electronics part suffix E plus K suffix L, so lattice part. So these two mechanism or these two thermal conductivities are there to conduct heat in solid. So electronic component part is there. So when we consider the electronic component part, so that is your thermal conductivity K, which is a material property. So when it will be a material property, so definitely if you think that heat is conducted in a solid, which is the shape or size of the fluid is reasonably what say a finite size. So if the size is finite, that means macroscopic size. In that case, the thermal conductivity K here, which is the material property, it completely depends on the material. But if we think that if the solid is very small, say microscopic level, the size of the solid is very small, in that case K may depend on the size of the solid. Okay. So here you just think, so K, that is your thermal conductivity in macroscopic way, so it is a material property. But if you think in microscopic way, so it may depend on the size of the solid. So it has two components, that is your electronic component and lattice component. That means energy transfer in solid or energy flow in solid due to the electronics part or due to the electrons, due to the free electrons movement. So due to the free electron movements, or you can say here, so migration of free electron. So due to the migration of free electrons, energy will be transferred inside the solid. So that part is called the electronics part of heat conduction. And for this, here thermal conductivity component has been written here. So that thermal conductivity component is called the electronic component of thermal conductivity. So that means free electron in solid are present So due to the free electron or due to the movement of free electron, energy will be carried out in the solid. And for that, this aspect, the electronic component of thermal conductivity has come. So whether it is clear or not? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
It is okay?
Yes, sir. Yes, sir.
So if any clarification is required, you just call, you inform me. Okay, so I will try to explain. Now another part, lattice part, if there is no free electrons or say heat transfer takes place in solid due to the temperature variation. So temperature is responsible here to conduct it. So energy is always transferred from higher energetic molecule to the lower energetic molecule. So due to this, so lattice vibration may take place. So lattice vibration may take place if the energy or heat is conducted in solid. So that part, so that is your lattice vibrational part for this energy transfer. So thermal conductivity is called the lattice component of thermal conductivity. So two components are there, that is electronic component of thermal conductivity and lattice component of thermal conductivity. Okay, so that I think it is clear, very simple. Now you can think K, that is your thermal conductivity. This thermal conductivity is responsible to conduct heat in solid or in fluid at rest. So depending upon the material condition, K definitely depends. So K value changes, or K property of K changes depending upon the material considered. Say if the solid is isotropic. So in that case, do know isotropic solid? That means thermal conductivity, or here thermal conductivity does not depend on direction of heat transfer. For isotopic solid, thermal conductivity does not depend on the direction of heat transfer. Okay. So for isotopic solid, K is the thermal conductivity, it is a scalar quantity. So it is a scalar quantity. We know in your 12th level that K is the thermal conductivity, which is a scalar quantity. For isotopic material, it is a scalar. Okay, understand? And another material is there for anisotropic. For anisotropic material, K or heat transfer depends on the direction, or thermal conductivity depends on the direction of heat transfer. So for anisotropic material, thermal conductivity is not a scalar quantity. It is a tensor quantity, like stress. Okay, so it is a tensor quantity for anisotropic material. It depends on the direction of heat transfer. Thermal conductivity depends on the direction of heat transfer for anisotropic material, and for isotopic material, K here does not depends on the direction of heat transfer. So it is a scalar quantity. For anisotropic material, K thermal conductivity is not a scalar quantity. It is a tensor quantity, second order tensor. So it is a second order tensor. Okay. So just initially you can think K for isotopic material. So for isotopic material, K is a scalar, definitely, and K may depend on the temperature or partial coordinate. Okay. So or K may be constant. So three possibilities are there for considering K. So generally in practical situation, in actual situation, K depends on temperature. So if you change the temperature, so K value, thermal conductivity value changes. Okay. For isotopic material, it is a scalar quantity. It may be constant or it may be variable depending upon the material chosen. Okay. So if it is a variable, so K depends on temperature or K depends on the coordinates. If we consider say Cartesian coordinate system XYZ, K is a function of XYZ. Or if we consider K, which is a function of temperature, so K depends on temperature. Now, definitely some question will come in mind. So when temperature changes, thermal conductivity increases or decreases. Okay, in most of the metal, the with the increase in temperature, thermal conductivity decreases. So before that, I think little bit explanation is needed here. K, it has two components, electronic components and lattice components. When these components are comparable magnitude and when this component, say, K is much greater than KL or KL is much greater than K. KE, that is energy transfer, this component has come due to energy transfer in solid by free electron, or free electron will carry energy from one place to another. So due to this physical aspect, this Ke term has come, this term. And lattice vibration, so every solid has lattice. So due to temperature, lattice will vibrate, and due to vibrational lattice, so energy will be conducted in solid, and for this scale term has come. So lattice vibrational part has come into this. So that means for all solid, so this part should be there, KL should be there. KL should be there, and Ke means metal. If free electrons are present, then Ke should be there. So electronic part of thermal conductivity is there if metal having free electron. If a metal having free electron, so Ke is there. So that means here, so depending upon the situation, K, okay, that is Ke plus KL. So KL should be there always, and Ke depending upon the free electron present, Ke will be considered or not. If free electrons are present, then if you think magnitude, Ke and KL, if we compare these two values, so definitely Ke will be much greater than KL. So that means for metallic substance, so for metallic substance, free electron should be there, and for the free electron, Ke value much greater than K. So here Ke for metallic, substance or substances, Ke value, that is your electronic component of thermal conductivity. So this value much greater than Kl. So definitely in this case, for metallic substances, we can consider K equal to Ke. We can consider here K equal to Ke. So in this situation, K equal to Ke. And for non-metallic substance where free electrons are not there, so lattice vibrational part will dominate. So in that case here,
Greater than K.
yes,
So the KL was lattice will be greater than the electronic force.
definitely Ka must be greater than the Ke. Must be greater because there is no free electron, so Ke is not there. Ke equal to 0 in that case. So only Kl is there. So K, that is your thermal conductivity, is equal to the K. Okay. Now, if you increase the temperature for isotopic material, so K is there. This is a scalar quantity. If you increase the temperature of the solid, then for metallic substances, K is responsible, or contribution of K is much greater than Kl. So in that case, K equal to Ke. If we increase the temperature of the metallic substances, then thermal conductivity of metallic substances will decrease with the increasing temperature. In most of the metal, this situation, this thermal conductivity reduces or decreases with the increasing temperature, except aluminum. If we increase the temperature, thermal conductivity increases. Okay. So when this condition will be satisfied, when it is true, if we increase temperature, the thermal conductivity of a metal reduces. When? That means if we consider say room temperature, then if we increase the temperature, or higher temperature if we consider, then if we increase the temperature further, your thermal conductivity reduces. Now, cryogenic temperature is there. Cryogenic temperature, which is lesser than the minus 250 degrees centigrade. And in that temperature zone, if we keep the material and if we increase the temperature in that temperature zone, in cryogenic temperature zone, then thermal conductivity always increases with the increasing temperature. In cryogenic temperature range, if we increase the temperature of a solid, then or of a metal, so thermal conductivity always increases in cryogenic temperature range. So whether it is clear or not? Hello?
So what is
Yes,
the
sir.
temperature range down?
Huh?
So what was the temperature range you told?
What?
Said the temperature range.
So temperature range for cryogenic.
Yeah, yes, the term cryogenic. Okay.
So I already mentioned that the temperature is lesser than minus 250 degrees centigrade. So that means what range is there? Minus 250 degrees centigrade to minus 273. That is your minimum temperature. So within that temperature range, if we increase the temperature of a solid, the thermal conductivity always increases. Understand my point? Hello, Mr. Raj?
Yes, sir.
Yes, sir. Yes, sir.
স্যার
Yes.
স্যার টেম্পারেচারটা বাড়ানোর সঙ্গে সঙ্গে তো ইলেকট্রনের মানে এমন কি হচ্ছে যার জন্য ওটার আমাদের
যার জন্য কি
কন্ডাক্টিভিটি কমে
free
যাচ্ছে।
electrons are there, and I understand. So free electrons are there, and if the increase in temperatures in normal situation, say 200 degrees centigrade, then you increase say 250 degrees centigrade. In that case, motion of free electrons or movement of free electrons, obstruction of movement of free electron increases in that case. So it increases, so resistance to heat flow increases. As a result, thermal conductivity reduces. reduced of the cases, except aluminium, I mentioned. Understand?
ওকে স্যার,
That
ওকে স্যার,
means
মানে ওই
free electron
মোশনটা একটু
part, contribution, heat transfer due to free electrons reduces with the increase in temperature in normal situation. And in cryogenic temperature, so reverse phenomena occurs. Reverse phenomena occurs. Now, so this is your isotopic material. K is there. K is thermal conductivity. It is a material property for finite shape of body. For infinitesimally small shape, or say microscale and nanoscale shape of the object. In that case, thermal conductivity depends on the shape also. Okay, for finite shape, thermal conductivity depends on it is a material property, and for infinitesimally small shape of solid, say nanoscale or microscale shape, in that case thermal conductivity depends on shape also. Now this is your isotopic material, and K is there, so it is a material property. And how this K can be determined? So K is needed if you want to calculate the conduction heat transfer in solid or in fluid at rest, then K should be required. So how K can be obtained? So what logic is there, and what steps should be there to determine K? So theoretically it is not possible to determine K. So experimentation may be needed to obtain the thermal conductivity. Understand my point? Hello?
Yes, sir.
Yes, sir.
Okay. So experimentation will be required here to determine K. If we know K, then you can determine or you can calculate the conductive heat transfer. So obviously, to calculate the conductive heat transfer, so law should be considered, Fourier's law of heat conduction should be considered for that. The Fourier law of heat conduction should be considered to determine the heat transfer rate if K is known, and K should be determined by considering from the experimentation. From the experimentation, K should be determined. K is known, then we can proceed to calculate the heat transfer rate theoretically. Okay? Hello?
So for solids, can we say that
Yes.
thermal conductivity will be a geometric property?
What?
So for solids, thermal conductivity will be a geometric property.
Is it? Material property. Huh?
Will it be a geometric property? Can we say like that?
What? So K is a material property for solid. So which one? So if the solid shape is finite, finite means what? Finite body shape.
Yes.
So in macroscopic level, if you think that it has some finite dimension, then thermal conductivity of solid depends on it is a material property. Sorry, it is a material property, and if the solid is shape is very small, it is infinitesimally small in micro and nanoscale shape. In that case, thermal conductivity depends on the shape of the body also. Okay. Hello.
স্যার ল্যাটিস ভাইব্রেশন মানে কি, মানে ওই ল্যাটিসের মধ্যেকার বন্ডগুলোর ভাইব্রেশনটা নাকি?
হ্যাঁ, তখন হচ্ছে তোমার ওই শেপের উপর ডিপেন্ড করতে পারে সেই সিচুয়েশন। তো এমনি তো মেটেরিয়াল উপর ডিপেন্ড করছে, তার সাথে সাথে শেপ ফ্যাক্টর উইল কাম হিয়ার, কাম ইন দ্যাট কেস। নাও so K is there. I already mentioned, K for solid, metallic, non-metallic. So metallic cases, if we increase the temperature of solid, thermal conductivity reduces except aluminum. In non-metallic substance, or insulating material. In that case, if we increase the temperature, so definitely thermal conductivity increases. So for non-metallic substance, so which aspect is there? So lattice vibrational part is there. Due to lattice vibration, energy will be transferred in solid. So that energy is called the conduction energy. Okay. So lattice vibrational part increases with the increase in temperature. As it increases, so thermal conductivity of non-metallic substance or insulating material, thermal conductivity increases with the increase in temperature. Clear? Hello? Now,
Yes, sir.
so it is very simple. And another thing, say fluid, say liquid and say gas, liquid and gas. So for liquid, thermal conductivity, if we increase the temperature in most of the liquid, thermal conductivity reduces. In most of the liquid, thermal conductivity reduces except water. So for water, initially thermal conductivity increases with temperature, and then at a particular temperature thermal conductivity becomes maximum. Then with further increase in temperature, thermal conductivity reduces. Okay. Otherwise, thermal conductivity of liquid reduces or decreases with the increase in temperature. In case of gas, so thermal conductivity always increases with the increase in temperature. So for gas, so thermal conductivity K here, this K for gas is proportional to N into C bar into lambda. So this K, thermal conductivity of gases, depends on these three parameters, N, C bar and lambda. So N is the number of molecules per unit volume. So this N represents the
স্যার একটু
number
নিচ থেকে
of,
স্যার একটু নিচে লিখবেন, দেখতে পাচ্ছি না স্যার, মানে ক্যামেরাটা আসছে না ওটা।
আসছে না? দেখো এবার দেখো তো আসছে কিনা?
আচ্ছা ঠিক আছে স্যার, ঠিক আছে।
ঠিক আছে? So you see here K varies or K proportional to N C bar lambda. This K for gases. Okay, using kinetic theory of gases, this K can be expressed in this way. K depends on N C bar lambda. So what is N? So N is the number of molecules per unit volume. So N represents the number of molecule per unit volume, and C bar is there, that is the mean speed of the molecules. Mean speed of the molecule, that is your C bar, and lambda is there. So lambda is the mean free path. So lambda is the mean free path. C bar is the average speed of the molecule, and N represents the number of molecules per unit volume. So K is proportional to these three factors, and if we increase the temperature, definitely K value increases. So K value increases in case of gas. In case of gases, so thermal conductivity K always increases with the temperature. So this is your
So what
K.
is C bar?
So C bar is the average speed of molecule. Average speed. Now, just we are talking about the heat conduction. Heat is conducted in solid or heat is conducted in fluid and rest. Okay. So before going to the elaborate discussion on this topic, I think three modes are there. Heat transfer, three modes are present. One is conduction mode, so heat is conducted in solid or in fluid. That is your conduction heat transfer. K is responsible for that. And convection heat transfer. So when convection heat transfer takes place, so definitely heat transfer takes place in fluid, or heat transfer takes place from the solid surface to the fluid, or from the fluid to the solid surface. And this heat transfer can be treated as convection heat transfer. So to determine the convection heat transfer, so difficulties are there. It is not so easy to calculate the convective heat transfer. So many aspects are there to understand the convection heat transfer, because heat transfer takes place from the solid surface to the fluid, or from the fluid to the solid surface, or in the fluid. So fluid is there, fluid motion is there. During heat transfer, fluid motion will be present. So during heat transfer, fluid motion will be present, and due to the motion of fluid, so complexity arises. Okay, understand? Now convection, again it has two components. Convection has two components here. You can write this is your convection, so it has two components. You can write here. So diffusion component is there in convection, diffusion, and another component is there. So that is your advection part. And convection depends on what? This convection depends on, so it has two components definitely. So convection depends on material fluid properties, depends on fluid properties. Convection depends on the flow properties. Convection depends on the solid surface. The solid surface or shape of the solid surface. If the shape of the solid surface changes, convection heat transfer changes. If the fluid changes, convection changes. And if the flow property changes, then convection changes. So convection depends on the shape of the solid surface. It depends on the fluid properties. It depends on the flow property. So flow property means what, Mister? So anybody can say what is flow property?
Compressible, incompressible flow.
Compressible.
Huh? Yes?
So compressible or incompressible flow.
And that is one property. So compressible fluid and incompressible fluid. Can you define it? What is compressible fluid? What is incompressible fluid?
So incompressible density doesn't change.
So when density does not change, so it is not a correct answer.
It change, but if it is less than Mach number 1.33, then it is called compressed.
So, Mach number what?
It's 1.3.
1.3.
Sir, 0.3, sir, 0.3.
0.3 or 0.4. Generally, we consider 0.4. If we consider this, then any fluid having Mach number lesser than 0.4, it will be incompressible fluid. So better you mention Mach number instead of density. Instead of density, better you can say Mach number. It will be the correct answer, obviously. So incompressible, compressible, so that is the fluid properties, not flow property.
Turbulent flow, laminar flow.
So turbulent laminar.
Turbulent flow, laminar flow, like this. Internal flow, external flow. So if the flow pattern changes, then in that case, your convection changes. Understand?
Yes, sir.
Yes. So here also this convection, the very interesting part and very little bit complexity is there to analyze the convection heat transfer because fluid flow is there. But it is very interesting and it has two components, that is your diffusion component and advection component. And generally, to analyze convection heat transfer, we have to determine the convective heat transfer coefficient H. So convective heat transfer coefficient is necessary to know or will be determined by using some analysis, and that H is required to calculate the convective heat transfer rate. So H is there, that is your convective heat transfer coefficient, and generally another dimensionless number has come. That number is called Nusselt number. Okay, we generally determine Nusselt number for calculating the convective heat transfer rate. So Nusselt number is required to know, and definitely complexity is there. So we have to consider three equations, and if we solve these three equations, say continuity, momentum, and energy, so three equations will be formulated, and we have to solve these three equations simultaneously in order to obtain the temperature distribution in fluid. Then we can get the Nusselt number, or we can get the heat transfer coefficient H. Heat transfer coefficient H we can get, and if H is known, then everything will be known. So using a Newton law of cooling, we can calculate the convective heat transfer rate. So H is the convective heat transfer coefficient. If H is known, then we can easily determine the convective heat transfer rate by considering the Newton law of cooling. Okay, so you know that Newton law of cooling. So before that, better here we want to explain these two aspects, that is diffusion aspect and advection aspect. So what is diffusion? So diffusion means it is a conduction part. So conduction part means here, so diffusion and conduction there is no difference. So it is a conduction part. So when convection heat transfer takes place, when convection heat transfer occurs, during that time or during that phenomena, so diffusion phenomena is also there. Means conduction phenomena is also there. That means convection, heat transfer takes place in fluid. This part, diffusion part, heat transfer takes place in fluid due to the temperature gradient existed. So in order to obtain the diffusion part, so heat transfer phenomena is there, and that heat transfer phenomena occurs due to the temperature gradient present. And there is no bulk motion of the fluid in that case. So no bulk motion of fluid is there. Heat transfer takes place within the fluid due to the temperature variation existed or due to the temperature variation. So in that case, the diffusion phenomena is there. So diffusion phenomena means diffusion heat transfer means here. So heat transfer in fluid due to the temperature variation or temperature gradient existed, and at that time there is no bulk motion of the fluid. So there is no bulk motion of the fluid particle. Heat transfer takes place in the fluid due to the temperature gradient existed. So that is your diffusion part. So diffusion part is similar to the conduction part, or both are same. And advection part, so fluid particles are there, fluid motions are there. So energy will be carried out by the fluid particles. And due to motion of the fluid particle or bulk motion of the fluid particle is there, so bulk motion is there, so energy will be carried out by the particle, fluid particle. So during this phenomena of heat transfer is called the advection. So in convection, two terms, two aspects, two heat transfer aspects are there, definitely diffusion and convection. Now, in some situation, say advection term is not there. In some situation, advection term is not there. So in that case, mathematically, what we can say here? So advection is not there. So convection equal to diffusion. So that means we can say here. So convection equal to diffusion. That means diffusion term is there. So we can say it is a convection. Actually, we do not consider that in that situation. We do not consider convection in that case. If diffusion is not there. If diffusion, if advection is not there, we do not consider convection equal to diffusion. We do not consider convection in that case. We should consider the conduction if advection is not there. If advection part is not there, then we should consider the heat transfer mode is conduction mode or only diffusion mode. It is not convection. So in case of convection, so this term should be there. Advection term should be there. And if you think in this way, say diffusion is not there. So heat transfer takes place in fluid, there is no diffusion. So in that case, convection equal to advection theoretically. So mathematically you can say convection equal to advection. Actually, if advection is present, diffusion term should be there. Whether it is clear or not. Hello?
Yes, sir. Yes, sir.
Yes, sir.
So, say you assume that initially, so there is no advection. That means convection equal to diffusion mathematically. Or from this mathematical expression we can say. So in that case, we never say this mode of heat transfer is called convection. We say it is conduction or diffusion. Okay. In the second case, say diffusion is not there. Practically, only advection is there. It is not possible. When advection is present, diffusion should be there. So that means convection, that is equal to diffusion plus advection. So diffusion part should be there along with advection, or advection should be there along with diffusion. So that is called convection heat transfer. So in convection heat transfer, diffusion, both diffusion and advection should be there. Now another mode is there. Yes.
স্যার বলছি অনলি অ্যাডভেকশন যদি থাকে এরকম কোনো কেস আসতে পারে তখন?
না, এরকম কেস আসবে না, তো জন্যই বললাম তো। তোমার এখানে টেম্পারেচার গ্রেডিয়েন্টের একটা ম্যাটার প্লে করে না, যে ধরো টেম্পারেচার গ্রেডিয়েন্ট এক্সিস্ট করছে তবেই তো হিট ট্রান্সফার হবে। টেম্পারেচার ভ্যারিয়েশন ইজ দেয়ার, সো diffusion part should be there. In convection, diffusion part should be there if advection is present. So that means convection, it has two components, diffusion and advection, and these two parts should be there. Understand? কি বলতে চাইছি? Hello?
হ্যাঁ স্যার।
Yes, sir, understand.
Okay. Now another simple mode, I will explain elaborately later. So little bit complexity is there to analyze convection heat transfer. Now radiation heat transfer. So that heat transfer is also studied in your class 10, 12th level. So radiation energy, energy emitted of a body due to its temperature. So no medium is necessary for the radiation heat transfer. So a body having temperature greater than minus 273 degrees centigrade emits thermal radiation. So you know that part. So two mechanisms are there to analyze radiation heat transfer. One is Maxwell electromagnetic wave theory and another one is Planck's theory. So these two theories have been used to analyze radiation heat transfer. If you want to determine the magnitude of radiation heat transfer, so Planck's theory should be considered. And if you want to analyze the radiation properties, then we should consider the Maxwell electromagnetic wave theory. So two theories are there to analyze radiation heat transfer. It is a little bit simple. Radiation heat transfer. Complexity is less. Okay, so I will elaborate in later stages. Okay, so that is your radiation part. So Maxwell electromagnetic wave theory. According to Maxwell electromagnetic theory, it is a radiation is an electromagnetic wave, and according to Planck's theory, it is a photon or quantum energy. So two theories have been used to analyze radiation heat transfer. Now we can focus or we can concentrate on the conduction heat transfer, where K term is there. K is the thermal conductivity, and I already mentioned that. So K is a scalar quantity for isotopic material, and it has two components. One is lattice component, another one is electronic component. And if we consider anisotropic material, so K is not a scalar, so it is a second order tensor. And thermal conductivity depends on direction of heat transfer. So before that, just I want to explain here what is K for anisotropic material. This is anisotropic material. So K is there. How this K depends on the direction of heat transfer. So 9 components are there. For anisotropic material, thermal conductivity, this thermal conductivity has 9 components. And generally, this K is can be expressed in a matrix form. It is a second order tensor. You can express in this way. So it is a matrix, and two suffixes are there, like stress. Two suffixes are there. So generally, K is expressed in this way. So K11, that is first suffix 1, second suffix is also 1, and K12 is there, first suffix 1, second suffix 2, and third one K13. Similar fashion here, you can write K21, K22, and K23. And the last row, you can write here, say K31 and K32, and this is your K33. So 9 components are there for anisotropic material, thermal conductivity. And here, thermal conductivity depends on direction of heat transfer. So how thermal conductivity dependent on the direction of heat transfer. So what is suffixes? So 1 is there, 1 2 is there, 1 3 is there. So first suffix represents the direction of heat transfer. So direction of heat transfer, you can consider say X Cartesian coordinate system if we consider. Then X, Y, Z, that is your coordinate, and first suffix 1, we can say x coordinate. X coordinate means, so heat transfer takes place in the x direction. Heat transfer takes place in the x direction for this thermal conductivity. So 1 is there. So 1 suffix 1 are there here. So this is K1, second one also K1, and third thermal conductivity component is also K1. So these three components or thermal conductivities are responsible to conduct heat in the x direction or in the one direction or in the x direction. So these three thermal conductivities are responsible to conduct heat in solid in the x direction. Okay. And second suffix is the temperature gradient suffix. So temperature gradient. So already I consider 1 means say x coordinate. That means temperature gradient is present in the x coordinate. So if we consider say temperature T, then temperature gradient in the x coordinate means del T by del x. So this temperature gradient is responsible to conduct heat in the x direction. Okay. So if
Yes,
you want to, yes. So if you want to determine the heat flux, okay, then we should consider K into thermal conductivity. K into temperature gradient. So that means if we consider this component of thermal conductivity, say K11 for understanding, then you can say right here, or you just try to understand here, say K11 into temperature gradient. Temperature gradient, which temperature gradient should we consider here? So second suffix. Second suffix means here, so if we consider 1 equal to x, then temperature gradient del T del x. So if we multiply this temperature gradient, then you will get the heat flux, which is acting in the one direction, which is acting in the x direction. So K11 into del T del x. So using Fourier's law of heat conduction, we can write here K11 into del T del x, and negative sign should be considered here. Negative sign. So this factor represents the heat flux, which is acting in the x direction for the temperature gradient del T del x. Okay.
yes,
So
sir.
just try to understand here. So K11 means K1 is the first suffix. First suffix represents the direction of heat transfer. So this direction means here the x component heat flux in the x component. So that means if we write better way, say Q suffix x means here component of heat flux in the x direction. This is Q, small q represents the heat flux. And suffix x means in the x direction and in the one direction. So this heat flux acting in the x direction for the thermal conductivity K11. So for the thermal conductivity K11, the heat flux occurs in the x direction. That can be obtained by considering this expression equal to minus K11 into del T del x. So I already mentioned that. So 3 K's are there whose first suffix is 1. So that means another thermal conductivity component is there. So due to this thermal conductivity, heat transfer takes place in the x direction, or heat flux takes place in the x direction. That can be obtained. We have to add this component value So it will be negative sign again from the Fourier's law of heat conduction, and K12 is there, K12 should be there, and 2 is there. 2 means here in the y direction, temperature gradient in the y direction. So temperature gradient in the y direction is responsible to conduct heat in the x direction. In case of anisotropic material, you know, here temperature gradient y direction is responsible to conduct heat in the x direction, and that value can be obtained in this way. So minus K12 into temperature gradient 2 means that y direction into del T by del y. And another component is also there, K1, K13. So we have to include this component here, minus K13 into temperature gradient in the z direction. So 3 means here z. So it is very clear that, you know, 3 components are there for conducting heat in the x direction. So that is your Qx. Qx is the heat flux in the x direction for anisotropic material, and equal to minus K11 into del T del x, minus K12 del T del y, minus K13 del T del z. So physically what we can say here? So this first term, there is no problem. So K11, you know, temperature gradient del T del x exists in the solid, and for the temperature gradient del T del x, we know that heat transfer takes place in the x direction, so there is no problem. The second case, this is your component of heat flux K12, and this K12 component into temperature gradient in the y direction, if we multiply, then we can get the heat flux component in the x direction. That means the temperature gradient in the y direction, for this temperature gradient, heat transfer takes place in the x direction. So that can be obtained by writing this mathematical expression. So that is K12 into del T del y. And K13, that is another component of thermal conductivity, and into temperature gradient in the z direction, we multiply, so that quantity will get the heat flux or heat transfer in the x direction. So that means total heat transfer or heat flux here in the x direction, that is equal to minus K11 into temperature gradient minus K12. 2 is represents the temperature gradient. So we have to multiply the temperature gradient in the y direction and minus K13 into del T by del z. So this is your Qx, that is your heat flux component in the x direction. So similar fashion, if you want to write the heat flux in the y direction for the anisotropic material, so it will be here Qy, that is equal to minus, so y means the direction of heat transfer in the 2 direction. So 2 means here thermal conductivity first suffix 2 should be there. So this is 2 should be there. These 3 components should be considered in order to determine the heat flux in the y direction or heat transfer rate in the y direction, whatever. So here heat flux in the y direction we want to determine. So we should consider these 3 components of thermal conductivity, and it will be the mathematical expression will be obtained by applying the Fourier's law of heat conduction, and it will be here minus k into 2 1. So 2 means y and 1 is there. 1 here, second suffix is the temperature gradient in the x direction. So we should multiply this temperature gradient in the x direction, say del T by del x. Then second component K22 second component this one into temperature gradient in the y direction, and K23 is there into temperature gradient in the z direction. So this is your heat flux in the y direction for anisotropic material. So similar fashion, you can write here say Qj heat flux in the z direction minus K into 31 into del P by del x minus K into 32 into del P by del y minus K into 33 into del P by del z. So that means here anisotropic material, so thermal conductivity depends on direction of heat transfer, and 9 components of thermal conductivities are there. 9 components are responsible to conduct heat in solid. And here first suffix 1 thermal conductivity responsible to conduct heat in the x direction. First suffix 2 thermal conductivities are responsible to conduct heat in the y direction. First suffix 3 component of thermal conductivities are responsible to conduct heat in the z direction. And mathematical expression is this, and this mathematical expression has been written by applying the Fourier's law of heat conduction. Okay,
Sir.
Yes, please.
বলছি এখানে কি কোনো অ্যাজাম্পশন করে নেওয়া হয়েছে যে সলিডটা মোশনে থাকবে না স্টেশনারি ওয়েতে থাকবে এটা করার জন্য?
না, এইটা করার জন্য কোনো রকম আমি অ্যাসাম্পশন করিনি. Obviously one assumption is necessary. You are absolutely correct. So one assumption is needed here. So this mathematical expression is valid for the stationary solid, definitely.
Okay, sir.
So why the minus sign is being used in the equations? So why the minus sign is used in the equations, sir? What is the significance of this minus sign, sir? Why are you putting the minus signs in before?
I think you know these things better. You know these things better. So why negative sign? So everybody knows.
Sir, is there any resistance case?
Huh?
না বেশি থেকে কমের দিকে হিটটা ফ্লো হয় না।
বেশি থেকে কমের দিকে গেছে উল্টো হচ্ছে।
Okay, just I want to know from you. So why negative sign is required?
So
when you apply,
হিট ট্রান্সফারটা হবে
just moment. So when you apply the Fourier's law of heat conduction, so when Fourier's law of heat conduction can be applied in order to obtain the conductive heat transfer rate, then we can apply the Fourier's law of heat conduction. So what is Fourier's law of heat conduction? This is your Fourier's law of heat conduction. So Joseph Fourier, the mathematical physicist, has given one mathematical expression for heat transfer rate. And this mathematical expression has been given based on the experimental observation. So there is no law used to investigate or to determine the law, determine the Fourier's law of heat conduction. So no laws have been considered here. So using experimentation, Joseph Fourier, the mathematical physicist, had given one mathematical expression for heat transfer or heat conduction rate or heat flux. So this is your mathematical expression, and negative sign has been considered. If we apply the Fourier's law of heat conduction, you should always consider negative sign. Why you should always consider negative sign? If we apply the Fourier's law of heat conduction, so negative, if you do not consider the negative, then it will be wrong. So why negative sign is required? So everybody knows, heat transfer takes place from the higher temperature to lower temperature. So if heat transfer takes place from higher temperature to lower temperature, your temperature gradient is negative. So here del T del X or del T del Y, del T del Z, all are negative quantity. So in order to obtain the positive quantity, positive value of heat flux or positive value of heat transfer rate, so negative symbol is necessary, because heat transfer takes place in a decreasing temperature, and temperature gradient in the x direction is negative. Yes, please. Hello. Hello. Any problem?
এই নেগেটিভ সাইনটাকে জাস্ট ডাইরেকশন ইন্ডিকেট করার জন্য ইউজ করা হয়েছে এটার জন্য।
So that is one aspect. So in order to obtain the positive quantity, that means for understanding, I think better if we plot here. Say this is your coordinate, and y-axis represents the temperature set. So this is x coordinate, just one-dimensional heat transfer. One-dimensional heat transfer here. Just we consider one-dimensional heat transfer. This is your temperature versus x, and you know the temperature variation is like this. So temperature in the x direction decreases. You know, temperature in the x direction decreases, your temperature curve is like this. Then obviously heat transfer takes place from higher temperature to lower temperature. So heat transfer or heat flux direction should be here, should be in this. So this is your heat flux, say Qx. Qx, the heat flux direction, and it is acting in the positive x direction. The positive x direction, Qx is acting. Now, if you want to apply the Fourier's law of heat conduction, then Qx equal to here Qx, that is equal to minus K into temperature gradient. So temperature gradient in the x direction, you know, here temperature is only function of x. As temperature is only function of x, here we write here minus K into, instead of del, you can write here. So total derivative can be written here, can be considered here. So minus K into dt dx. So when this expression is true, so this expression is true when T is only function of x. So what possibilities are there? So this is your temperature. So temperature, if we consider Cartesian coordinate system, so temperature may be function of x, y, z and time. Okay. So in this case, here temperature T is only function of x, only function of x. In general, if we want to write the general expression, then here temperature T, so this is the general case, temperature will be as a function of x, y, z, and t. So if we consider this temperature, so general expression, then your Fourier's law expression will be minus K into del T by del X. Minus K into del T del X if we consider this. And this heat flux Qx depends on time t. So if you change the time t, then Qx changes. So Qx is not independent on time. So in this case, Qx depends on t. So here Qx does not depend on the t. here because it is a steady state situation, steady flow situation. So only temperature is only function of x. There is no time. There is no time, and your mathematical expression, the first mathematical expression is correct for temperature is only function of x, and second mathematical expression is a general expression. Temperature may be function of x, y, z, and t, and your Fourier's law of heat conduction. By applying the Fourier's law of heat conduction, if you want to determine the heat flux Qx, that is equal to minus k del T del x. So when this equation is valid, definitely for isotopic material. For anisotropic material, so we have to consider again three components we have to consider. So this is valid for isotopic material, and another assumption is necessary here. Your solid is stationary. In that case, the solid is stationary. If solid is not moving, the solid is stationary. Then Qx equal to minus k into del T del x, and this expression is valid for isotopic material and solid is stationary. Clear? And this Qx, the last term here, depends on time. So this is depends on time. So that means heat flux components depends on time. So with the change in time, so Qx value changes. Qx value changes the second one expression.
স্যার এই ক্ষেত্রে মানে সেকেন্ড ক্ষেত্রে আইসোট্রপিক মেটেরিয়ালের ক্ষেত্রেও তো মাইনাস কে ডেল টি ডেল এক্সটা তো হচ্ছে, কিন্তু তার সঙ্গে ডেল টি ডেল ওয়াই ওই পার্টগুলো আসছে না কেন?
ওই পার্টগুলো আসছে না। ওই পার্টগুলো কখন আসবে? if we consider anisotropic material.
অ্যানিসোট্রপিক হলে তো কে 1112 এগুলো আলাদা হয়ে যাবে, কিন্তু মানে কি বলবো, ওয়াই এর চেঞ্জের জন্য তো এক্স ডাইরেকশনে আমার হিট ফ্লো থাকতেই পারে আর কি।
In this case,
আইসোট্রপিক ম্যাটেরিয়ালের ক্ষেত্রে
for isotopic material, so for isotopic material, if temperature gradient exists in the x direction, that temperature gradient responsible to conduct heat in the x direction only. For isotopic material, so del T del x is present, and that component of heat flux in the x direction, if we want to determine the component of heat flux in the x direction, so that heat flux can be obtained by using this mathematical expression. তুমি যদি এখানে apply করো minus k into del T del y, that component is responsible to conduct heat in the y direction, not x direction for isotopic material. For anisotropic material, x.
স্যার আমাদের তো স্যার সাবস্টেন্সিয়াল ডেরিভেটিভটার কথা বলছে, মানে ওই টেম্পোরাল ডেরিভেটিভ আর কনভেক্টিভ ডেরিভেটিভ যেটা আছে ওই দুটোর
সাবস্টেন্সিয়াল ডেরিভেটিভ কখন আসে? when substantial derivatives has come.
মানে স্যার যখন মানে কি বলবো একটা
fluid motion is there, if fluid motion is there, if velocity is there, fluid velocity.
yes
So in this case no velocity. So just I am mentioning here the solid is stationary, not fluid, solid. Solid is moving, that means solid is moving, not fluid is not there. So when substantial derivative will come? When fluid motion is there. Substantial derivative or total derivative, that is different issue. So I will explain in the convection analysis. When we do the convection analysis, in that case substantial derivative terms has come. So here no substantial derivative. So this expression has been written here, Qx equal to minus k del T del x. Here solid is stationary and solid is isotropic. So two assumptions have been considered to write this mathematical expression. One assumption is solid is isotropic. The second assumption is solid is stationary. So another assumption is also there. Third assumption, here speed of propagation of heat in solid is very high, goes to infinity. In that case, your Fourier's law of heat conduction is valid. So that means total three assumptions have been considered to write this mathematical expression. The first assumption, the solid is isotropic. Second assumption, solid is stationary. Third assumption, speed of propagation of heat in solid is very high or goes to infinity. Okay, so that means limitation is there to consider the Fourier's law of heat conduction. So what limitation? Fourier's law of heat conduction. If the speed of propagation of heat is very high, if it goes to infinity, in that case, Fourier's law of heat conduction is valid. If the speed of propagation of heat is finite, in that situation, we cannot apply the Fourier's law of heat conduction. Whether it is clear or not? Hello?
Yes, sir.
Yes, sir.
কি করে মানে মাপে ওটা
হ্যাঁ বলো।
মানে স্পিডটা দেখবো কি করে প্রপাগেশনের ওটা হিটের?
এটা তো আর কি দেখা যাবে, তুমি এখানেও কি যে ক্যালকুলেট করছো, তুমি টেম্পারেচার গ্রেডিয়েন্টটা কি করে পাবে?
না ওটা তো স্যার দুদিকের টেম্পারেচারটা মেপে নিলেই তো পেয়ে যাবো যে এত গ্রেডিয়েন্ট।
না সে তো তুমি সেখানে টেম্পারেচার গ্রেডিয়েন্ট তুমি যেটা বলতে চাইছো যে টেম্পারেচার ইউজিং থার্মোকাপল ইট ইজ পসিবল টু নো, ইউজিং থার্মোকাপল ইট ইজ পসিবল টু নো। হ্যাঁ, সেখানেও আর কি মেজারমেন্টের টেকনিক আছে। তো ইন দ্যাট কেস if we apply the non-Fourier heat transfer, so time lag aspect should be considered. Time lag. If time lag equal to 0, it will be the Fourier's law. We can apply the Fourier's law for the time lag equal to 0. If there is a time lag or relaxation time, then we should consider non-Fourier heat transfer. So many laws are there to consider the non-Fourier heat transfer. So in this
মানে আমরা ধরে নিচ্ছি মানে এক এন্ড থেকে অন্য এন্ডে মানে লাইটের স্পিডে চলে যাচ্ছে নাকি, মানে খুব স্পিডে ইনফাইনাইট স্পিডে চলে যাচ্ছে,
খুব স্পিডে যাচ্ছে। There is no lagging. There is no lagging for the movement of heat transfer.
কিন্তু সে এমনি তো একটু টাইম তো লাগবে।
থিওরি অফ রিলেটিভিটির কনসেপ্ট চলে আসছে।
হ্যাঁ,
সেখানে থিওরি অফ রিলেটিভিটির কনসেপ্ট চলে আসছে।
কনসেপ্ট ওই রকম ভাবে আসছে না। I will explain later. I will explain how this term can be modified if we apply the non-Fourier heat transfer. So I will explain. Definitely I will give the mathematical explanation. Now at this moment, just try to understand why negative sign. That is very important here. So why negative sign has been considered if we apply the Fourier's law of heat conduction. So negative sign is there. I already mentioned that, if this temperature variation is like this, temperature changes in the x direction and temperature decreases in the x direction, then if we apply this minus k into del t del x or this one, whatever, so temperature gradient is negative. So here qx means heat flux acting in the x direction, which is positive quantity. So in order to obtain the positive quantity, we should consider the negative sign. So that's why I consider the negative. I use the negative symbol. So in other way, say your temperature variation is this. So with the increasing x, so temperature gradually increases in this way. So it is also possible. So depending upon the selection of coordinate system, you see there in the x direction, so temperature gradually increases. Okay, so that means from low temperature to high temperature, so temperature increases in the x direction. If temperature increases, so in this case, if we want to determine the temperature gradient, so dt dx is positive quantity in this case. So here dt dx is positive. So that means if we apply this qx, that is equal to k into dt dx. So you remove the negative symbol, negative sign, if removed, then what will happen? So qx will be positive quantity in this case, because dt dx itself positive. Clear? Hello?
Yes, sir.
Acha. If
Yes, sir.
positive, then what will happen? So qx is positive, dt dx is positive. That means we should consider, in this case, we may consider the qx that is equal to k into say dt dx. So whether it is correct or not?
Yes, sir.
Is it correct? We apply the Fourier's law of heat conduction. So Qx in this case, K into dt dx, because here dt dx is a positive quantity, so negative sign is not required. But we write in this way. Is it correct expression? Mr.
ডাইরেকশন ওয়াইজ নয়
কেন নয়? Why not?
স্যার কারণ
তাহলে
ফ্লাক্সটা
তো
অন্যদিকে যাচ্ছে স্যার।
আগের
কারণ
কেস আর এই
ফ্লাক্সটা তো
কেসের মধ্যে কেউ ডিফারেন্সই বুঝতে পারবে না, মানে
হ্যাঁ, তাহলে
Coordinates.
ডিফারেন্স আছে, ডেফিনেটলি ডিফারেন্স আছে। কি
হ্যাঁ।
ডিফারেন্স
আছে তো কারণ ফ্লাক্সটা
মানে
কোঅর্ডিনেট সিস্টেমটাকে তো অন্যভাবে নেওয়া হয়েছে।
হ্যাঁ, এটা তো সিস্টেমের যে ওরিয়েন্টেশন তো চেঞ্জ হয়ে যাচ্ছে না।
হ্যাঁ।
ওরিয়েন্টেশন চেঞ্জ হয়ে যায়, তাহলে কি মডিফিকেশনটা লাগবে?
মাইনাসটা দিতে হবে সামনে।
মাইনাসটা আমাদেরকে দিতে হবে। কেন এই ক্ষেত্রে দিতে হবে যে মাইনাসটা?
ডিফারেন্সিয়েট করার জন্য।
মানে আমার রুলটা হচ্ছে যেদিকে টেম্পারেচার কমবে সেদিকে তো হিটটা যাবে।
Logic here, you try to understand here. In this case, in the previous case, Qx, that is heat flux, acting in the positive x direction. In the previous case. So in this case, Qx acting in the negative x direction.
এটাই বললাম তো।
To differentiate this, so Qx is acting in the negative x direction. We should put the negative symbol, negative sign here. So negative sign should be considered, should be given here. So that means if we apply the Fourier's law of heat conduction, we should consider the negative sign. If we write Qx equal to K dt dx, in this case it will be wrong if we apply the Fourier's law of heat conduction. Whether it is clear or not?
Clear, sir.
ইয়েস স্যার।
হ্যাঁ, এবারে একটা ব্যাপার আছে যে ধরো তুমি যদি ম্যাগনিটিউড ডিটারমাইন করতে চাও, just only you want to determine the magnitude of heat transfer rate or heat flux. So in that case, we have to think whether dt dx or dt del x is, or temperature gradient is positive or negative. If it is positive, then negative sign should be omitted, should not be written, the negative sign, or negative sign should be deleted. Only consider the positive in that case. If you want to determine only the magnitude of heat transfer or heat flux in that case. But if we apply the Fourier's law of heat conduction in a derivation, then we should use the negative sign. Whether it is clear or not, বলো কোনো প্রবলেম আছে কিনা?
Clear, sir.
Yes, sir.
ঠিক আছে, এবার যদি বলো তোমাদের বলো। আজকে আমি মোটামুটি জাস্ট স্টার্ট করছি, তারপরের দিন আমি আরো একটু বেশি সময় নিয়ে অবভিয়াসলি ক্লাসটা নেবো। জাস্ট বলো তোমাদের যদি কোনো রকম কোনো ক্লারিফিকেশন লাগে। আমার মনে হয় তার আগে একটু বলা দরকার যে অলরেডি আই হ্যাভ মেনশন সাম অ্যাসাম্পশন। First assumption and first assumption, that means solid is isotropic. I mentioned that solid is isotropic. Okay. So I discussed what is isotropic material, what is anisotropic material. So using this concept or using the discussion here, okay, that assumption is valid. Solid is isotropic. Okay, no problem. And second one is assumption, the solid is stationary. If the solid is not stationary, then what modification will be required? If the solid is not stationary, if the solid is moving with a velocity, then another flux will come. That flux is called the convective flux or enthalpy flux. So we have to write another flux. If the solid is not stationary, it is having uniform velocity, then we have to modify this Fourier's law of heat conduction by using another flux. That flux is called the convective flux, or convective and or enthalpy flux. So that flux here rho into Cp into velocity term, say Vx direction, so velocity in the x direction, say Vx, and temperature is there. So rho Cp into Vx into T. So this is flux, rho Cp Vx into T. This flux is called the enthalpy flux or convective flux, and this flux has come due to motion of the solid, and here the solid velocity in the x direction, which is Vx, and T is the local temperature, and rho Cp, you know, the heat capacity. Heat capacity here, if we consider solid, Cp equal to Cv or C, whatever you write, and rho is the density. Rho is the density, and this flux, the convective flux, again, this flux has been written by considering the experimentation. But from the experimentation, this enthalpy flux expression has been written. Okay. So if the solid is not stationary, then your expression will be required to change, and in that case, Qx, that is minus K into del T del x, so temperature gradient is there due to temperature gradient, heat flux component, and this heat flux component has been written by applying the Fourier's law of heat convection. And for the motion of the solid, another flux has come. That flux is called the convective flux or enthalpy flux. And expression is this rho Cp Vx into T. Okay, so this term should be added if the solid is stationary.
লোকাল টেম্পারেচার বলতে স্যার?
So local temperature means the temperature already, if we consider a solid temperature depends on coordinate.
স্ট্যাটিস্টিক্যাল এভারেজটা নাকি?
Depends on coordinate. So any coordinate, any value of x. So Qx is there, you know, Qx, that is component of heat flux in the x direction. So there is no value consider of x. So depending the value of x, Qx value changes. Similarly here T has been taken here. T is a function of x. Okay. So if we consider x value or x value, so T depends on x. Say x equal to 0, T, you will get T value, and x equal to say 0.5, you will get another T value. So that local temperature should be considered. That means T is a function of x, that T should be considered. For understanding, say Qx, that is your heat flux in the x direction. Now you want to determine say Qx at x equal to 1. So that is equal to say minus K into say dt dx at x equal to 1 plus rho into Cp into Vx into T at x equal to 1. So here you see, so K term is there, dt dx term is there. So here dt dx depends on x. You just put x equal to 1, you will get the temperature gradient. So that temperature gradient should be considered. And rho Cp Vx into T is there. So Vx is there, whether Vx is variable or it is a constant. So definitely here, this expression is valid for Vx is a constant. So uniform velocity in the x direction.
Sir,
নন ইউনিফর্ম হলে কি হবে?
sir, cavity to uniform, sir.
Little bit modified, non-uniform এর কোনো এখন mathematical expression দেয়।
স্যার বলছি ক্যামেরাটা একটু নিচে কোন বোর্ডটার নিচের দিকটা দেখতে পাচ্ছি না।
আরে তুই দেখো এবারে দেখো। ঠিক আছে?
হ্যাঁ স্যার দেখা যাচ্ছে।
দেখো।
হ্যাঁ দেখা যাচ্ছে।
তবে তুমি যেটা বলছো নন ইউনিফর্ম ধরে কিন্তু এখনো সেরকম ভাবে এক্সপ্রেশনটা দেয়নি। এখানে ইউনিফর্ম ভেলোসিটি
দেয়নি, মানে বের করানো হয়নি।
এবারে বের করা হয়নি। এবার তুমি যদি সেই রকম ভাবে ভাবো যে এক্সটাও চেঞ্জ করে যাচ্ছে, ওই ভিএক্সটা চেঞ্জেস উইথ দি ভ্যারিয়েশন অফ এক্স, তাহলে এখানে ভিএক্স এর ক্ষেত্রে এক্সটাকে পুট করতাম। So if Vx changes in the x direction, in that case, we should put here generally বইয়েতে যেগুলো বলা আছে সবই বলা আছে ইউনিফর্ম ভেলোসিটি in the x direction or uniform velocity in the y direction. It is not a variable. It is uniform. Understand?
Yes,
So
sir.
যতগুলো বই আছে তাতে ইউনিফর্ম ভেলোসিটি বা ভাষাটা ল্যাঙ্গুয়েজটা ইউজ করেছে। বলো এনি কোশ্চেন, আমি নেক্সট ক্লাস আমি তোমাদের শেয়ারের সাথে কন্ট্যাক্ট করে আমি ফিক্স করব।
হ্যাঁ স্যার, আমি কন্ট্যাক্ট করে নেবো। স্যার আরেকটা কথা বলছি স্যার, আপনি অ্যাটেন্ডেন্স কি নিয়েছেন?
হ্যাঁ,
অ্যাটেন্ডেন্স কি আছে ক্লাসের আপনি নিয়েছেন?
তুমি কিন্তু আমাকে এটা হেল্প করতে পারবে অ্যাটেন্ডেন্সের ব্যাপারে?
স্যার আমি নিয়ে নিয়েছি অ্যাটেন্ডেন্সটা স্যার, আমার স্ক্রিনশট
আচ্ছা।
নেওয়া হয়ে গেছে। আমি কি স্যার আপনাকে এক্সেল শিটে বানিয়ে দেবো নাকি জাস্ট স্ক্রিনশট গুলো পাঠাবো?
তোমার যেটা সুবিধা হবে। আমি
আচ্ছা,
এখন নেবো না, আমি ক্লাসটা যখন এন্ড হয়ে যাবে সেই সময় নেবো।
ঠিক আছে স্যার, আমি বানিয়ে রাখছি। আমি আগের সেমিস্টারেও করেছি অ্যাটেন্ডেন্স কিছু 2-3 ক্লাসের।
তুমি এটা যদি করতে পারো, আমার তোমাদের এটাই বলার ব্যাপার যে আমি কিন্তু অ্যাটেন্ডেন্সের গুরুত্ব দিই।
আচ্ছা ঠিক আছে স্যার, বুঝতে পারছি।
মানে অ্যাটেন্ডেন্সের ইম্পর্টেন্সটা আমার কাছে আছে, কারণ কারো পারফরমেন্স খারাপ হলে আমি অ্যাটেন্ডেন্স ভালো থাকলে তাকে আমি ভালো মার্ক দিই।
বুঝতে পারছি স্যার।
ঠিক আছে?
হ্যাঁ স্যার ঠিক আছে।
আচ্ছা,
বলছি আপনি ওই অনেক আগে একটা সলিড সারফেসের ব্যাপারে বলছিলেন না, ওইটা মানে কি পাত্রটার সারফেসের কথা বলছিলেন?
কি বলো আরেকবার বলো।
ওই অনেক আগে ওই কনভেকশনের সময় একটা সলিড সারফেসের ব্যাপারে বললেন না, ওইটা কোন সলিড সারফেস মানে পাত্রটার কথা বলছেন?
ধরো তুমি এখানে জাস্ট ফর আন্ডারস্ট্যান্ডিং, সো আমার কাছে এইটা একটা সলিড সারফেস আছে। হিট ট্রান্সফার টেকস প্লেস ফ্রম দ্য সলিড সারফেস টু দ্য ফ্লুইড। এই যে সলিড সারফেস জিওমেট্রি অফ দ্য সলিড সারফেস, এইরকম একটা সলিড সারফেস। Instead of this, we can consider this solid surface, this one. দেখতে পাচ্ছ?
হ্যাঁ স্যার দেখতে পাচ্ছি।
দেখো শেপটা চেঞ্জ হয়ে যাচ্ছে, যদি শেপ চেঞ্জ হয় হিট ট্রান্সফার রেটও তো চেঞ্জ করে যাবে, কনভেকশন হিট ট্রান্সফার রেটও চেঞ্জ করে যাবে। তো সেই
যেটা
কথা
থ্রু দিয়ে হিটটা ট্রান্সফার হচ্ছে আর কি, সেটা সারফেসটা কথা বলে।
তার মানে ওই shape of the solid surface, convection heat transfer depends on the shape of the solid surface.
বুঝতে পারছি। আচ্ছা বই কিছু কি মানে কি ডাউনলোড করতে?
হ্যাঁ স্যার, বইয়ের ব্যাপারটা স্যার বইটা একটু বলুন।
OGSIC heat transfer, OGSIC basic approach সেটা ডাউনলোড করতে পারো, or Inkebara date heat and mass transfer, Inkebara and date, that book is also good. Or Schengel heat transfer, or Hallman, so many good books are there. I generally prefer OGSIC heat transfer, মানে basic heat transfer within the bracket.
স্যার স্পেলিংটা বলুন।
স্পেলিংটা বলুন
স্যার। আপনি একটু বলেন স্যারকে লিখে পাঠিয়ে দিতে পারবেন স্যার? তাহলে
আরে এই বইটা প্রতিশ দিদি যেমন
আমি দিলাম তো এই বইটা।
ওজি সিকটা দেখে যাই।
ঠিক আছে স্যার, আমি এটা জোগাড় করে নিচ্ছি।
আচ্ছা স্বপ্নিল একটু চ্যাট বক্সটা দেখ, মানে তোর হোয়াটসঅ্যাপটা দেখ একটু স্বপ্নিল।
হ্যাঁ দেখছি।
দাঁড়াও। এই যে দেখো বইগুলো আমি দেখাচ্ছি। So this one, heat transfer basic approach, written by OGSIC.
হ্যাঁ স্যার দেখতে পাচ্ছি। হ্যাঁ স্যার অ্যাকশন
Yes, sir. Yes, sir.
So second one, it is also very good book. This one. দেখতে পাচ্ছ?
এই বইটাও তো দিয়েছিলাম
স্যার। আমাদের এই মানে কোর্সটা তো শুধু হিট ট্রান্সফারই না, মানে মাস ট্রান্সফার নাই তো?
মাস ট্রান্সফার নাই, এই একটা বুক হলম্যান,
জেপি হল।
so any book, this is also very good book, this one, transport phenomena.
স্যার একটু দূরে করুন, বইটা হাফ দেখতে পাচ্ছি।
স্যার যে কোনো একটা বুক ফলো করলেই তো হলো।
হ্যাঁ স্যার যে কোনো একটা
Any book, I think you can
OGSIC.
follow either Inkebara date or OGSIC.
ওকে স্যার,
Okay.
ওকে স্যার।
তো তাহলে ক্লাসটা এখানে এন্ড হচ্ছে?
হ্যাঁ, এখানে এন্ড করে দিচ্ছি, তোমার পরে তোমার সাথে কন্ট্যাক্ট করে আমি দেখি।
ওকে স্যার, হ্যাঁ 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 শিওর স্যার, ওকে থ্যাংক ইউ স্যার।
ওয়েলকাম।
স্যার লিভ করলাম, হ্যাঁ
থ্যাংক ইউ স্যার।
থ্যাংক ইউ স্যার।
Thank you, sir.
ওয়েলকাম।